All right, how we doing, guys? Today we are gonna go ahead and start learning a couple of different things. We've got two goals that we want to work on. So our goals, first of all, we want to be able to take our full Lewis structures and we want to do two things. First, we want to be able to take that Lewis structure and form a skeletal structure. And then with that skeletal structure, we want to be able to write the formula. So if I were to give you a full Lewis structure, you can take it to the skeletal structure. And if I were to give you a skeletal structure, we could take it to our formula. Okay? The second thing that we really want to work on, and this is probably going to come tomorrow, you're going to want to try and name functional groups. So name or identify structural groups. Okay, so we are going to start. I'm going to kind of give you an example here to start with, and then we've got some a whole lot of practice that we'll be able to do. Some videos to watch that'll help us with this as well. But we're going to start with capsaicin. All right, so capsaicin is a relatively large molecule. We are going to start with our full Lewis structure of capsaicin. And if we do that, it's going to take a little bit. One thing that I'm going to point out as I am drawing this, we've got a lot of carbons on here. We've got a lot of hydrogens on here. And we're going to find when we write our skeletal structure, it's much easier because we can get rid of a lot of those carbons and hydrogens. Okay, so I'll show us how we do that in just a second here. The other piece that I'll point out as I am drawing this is that I am drawing this on blank paper. I highly, highly, highly recommend that you guys use blank paper to write our organic molecules. This can be some art paper that you buy. You can buy blank paper as a notebook. But really what I oftentimes end up using is just printer paper. So we always have printer paper available. I highly recommend that you use it because our molecules, we've got lots and lots of things to draw. It's much easier if we are able to not get encumbered by the lines, okay? So when I do this, you can see again, I've got so many carbons and hydrogens that this is going to take up the entire page going across. And when I'm drawing it, I get a little bit lost as well. So this is why we oftentimes will draw our skeletal structure instead. It condenses things down a whole lot, so we don't have to write nearly as much onto that structure. And I'm running out of space, so I'm going to write it a little bit smaller. So there is our full structure now. It is a lot. So let me go ahead and take this and write our skeletal structure instead. So if I go to write this as a skeleton, I'm going to have each of my carbons as a vertex. So over on the left-hand side here, I've got 1, 2, 3, 4, 5, 6 carbons. So I'm going to draw a 6-membered ring. I'm going to draw my double bonds between them. And then my hydrogens that are attached to just a carbon, I'm just going to ignore them. I'm going to assume that for each of those carbons, yes, I've got a hydrogen attached to them. They don't have any charges that I need to worry about, so I'm just going to assume, hey, I've got some hydrogens on there. So when I do this now, I end up with something that looks like this. And this is much easier to draw, as you can see. So to recognize what's happening here, I can see at my structure up here, I started with my 6-membered ring. I counted my 6 carbons, and I said, okay, there's 6 carbons in a ring. I'm going to draw my 6-carbon ring there. I'm going to put each of my double bonds on there, and then this is just an oxygen with a hydrogen on it. I'm going to put an OH. I'm going to put an OH here. Then I have a CH2. Well, that's just a carbon. I've got a vertex there. And then I have an NH, and then a carbon with a C double bonded to an O. So I've got my nitrogen here, carbon double bonded to an oxygen. Then I had 1, 2, 3, 4 carbons that just have hydrogens attached. Then I've got a carbon double bonded to another carbon. This hydrogen is on the opposite side of that carbon, so I'm going to put these two opposite sides. And then I have a carbon with 2 carbons attached, and each of those have hydrogens attached to them. So this is my skeletal form of my capsaicin. I can take this now and draw, or I can write out my formula. The way to do this, again, is to start with your carbons. Let's count each of our vertices. So 1, 2, 3, 4, 5, 6 we said on the ring, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. These ones on the end do count. So I'm going to have C17. Then I'm going to go to my hydrogens, and this is where it gets a little bit harder. I've got 1, 2 on those OHs, 1, 2, 3 that are left over on that ring. So that's 5. I've got 2 coming off of each of these, right? If I think about this carbon here, it's got 1, 2 bonds. Carbon normally has 4, so I'm assuming that the rest are hydrogens. So I'm going to add 2 more there. That brings me up to 7. This carbon has 4 bonds to it, so I don't need to worry about any hydrogens there. So now to not get lost, I'm going to count. I'm at 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then I've got 3 coming off of this, 3 coming off of that. So that means I have 24 hydrogens. And then I need to deal with my oxygen and my nitrogen. I've got 2 oxygens and 1 nitrogen, and that should be my entire formula. All right. So I'm going to go ahead and I'm going to pause there.